So this video is going to talk about um, continuous probability distributions. Continuous probability distributions come about from when we have a continuous random variable, such as height or weight or even age. My height is 5'6", but I'm really not 5'6". I'm probably 5'5.3276112 or some other value like that. I don't know what exactly it is, but we rounded to 5'6" because it's just easier to round. But the actual value could take on is a whole multiple of different values that we could get. And so these are what I can call continuous random variables, as opposed to discrete random variables that we looked in the past. And what I want to do is I want to look at random variables that create that happening. So we're going to look at this state here, and we have this graph here, which is the height of adults. And it looks like a fairly bell-shaped curve, not perfectly, but a little bit of a bell-shaped curve. We can look at other values, like how many sleep hours somebody gets. And that graph, if we look at that a little bit closer, that kind of has what we call a uniform distribution, where we have this all about the same value. In those, we get some people who sleep a lot less, some people who sleep a lot more, but the majority of us are kind of on this kind of uniform mode. Some other ones that we can look at, the amount of testosterone a person has. So you can see this is obviously not, it's more of a skewed right distribution. And we have a couple humps going on here. It's definitely not a bell-shaped curve that we'd like to see. We can have a couple other graphs that would do this. We can look at BMI of somebody. And again, you've got a couple humps going here. Definitely not a bell-shaped curve, or what we call a normal distribution. Nothing normal about normal distribution, it just happens to be there. We can also look at pulse rate. Pulse rate has more of, a little bit more of a unit of a normal distribution kind of place, a little bit of skewness going on. And there's lots of other variables we could look at here. Oops. If I look at systolic blood pressure, that one is really looking like we have a big hump, and then we're skewed off to the right. So these are the different types of random variables we can have that we work with. And now we're going to spend time on this thing called a normal distribution. And the only thing we spend a lot of time on it is it turns out a lot of the work we're going to do involves this normal distribution. And it's got this bell-shaped curve. It's taken me years to learn how to draw them this well. So don't worry about how well you draw them. Just try to draw them somewhat. If the center of this is your mean, the symbol for mean is this weird looking symbol called a mu. And the mean is always right at the center. It's also the same place as the median and the mode, because in a normal distribution, it's completely symmetric. So it's also the same place as the median is. And if we're going to talk about the mode, it would be the same place as the mode. If you go one standard deviation above the mean and one standard deviation below the mean, we get these things called these inflection points. Don't worry about what an inflection point really is. It's just kind of where things change. And you can see a lot of the data seems to be in here because there's a big group of the data there. The symbol for standard deviation is this Greek symbol sigma. And what I want to do is talk about what sigma does for us. The mean tells us where the center is. If I change the mean, it could move it over left or right, but otherwise the mean is just the center. The standard deviation is going to be a little bit different. If I have a really small standard deviation, then that distance over to your inflection point isn't very far. But if I have a much larger standard deviation, then that distance is longer, farther over. And so what I get is a much lower curve than I got with the other one. So I get a more flattened curve when I have a larger standard deviation, and a smaller, more peaked curve when I have a smaller standard deviation. So the mean mu tells the center, and the standard deviation sigma tells the shape. There's a formula that actually created that curve we saw on the other page. Don't worry about that formula. You're never going to use it. But it's there if you want to see what it was. But more importantly is, how do we find probabilities? So I want to find the probability of being between, let's say x being between my x is my random variable, and I want my random variable to be between two values. So if I have that going on, then what I could look at here is, again, I can look at my normal distribution. Here's my normal distribution. Again, the center is my mean. And if, let's say, A is here on my axis, so think of this as a horizontal axis here. So this might be the number A, and this might be the number B. Then that probability is this area between these two. And so it turns out it's the area under the curve is what that probability is. And that's what we want to find out. We want to know how much of the data, really what this is telling me is what percent of the data is in between these two lines. How much of the curve is here? And looking at this, just guessing, this looks like about, I don't know, 40% of the curve is shaded because there's a lot of the curve not shaded here and a lot not shaded here. So it looks about 40% of the curve. So what we want to do is be able to find those. And there's a rule called the empirical rule that helps us with finding those. A little bit. They give you approximations, and I hate the approximations, so I don't really use it very much, but I want to give you kind of an idea of what's going on. Again, we've got our center here. And if I go one standard deviation above the mean, so this is plus one standard deviation, and I go down one standard deviation below the mean, so down one standard deviation, so minus one standard deviation, the empirical rule tells me how much data is in this between these two lines. And the empirical rule tells me that it's about 68% of the data. If I go a little bit farther, if I go another standard deviation, so I'm 2 standard deviations above, or 2 standard deviations below, then the empirical rule tells me that there's about 95% of the data between here. And you can kind of see that. You can see that it looks like an awful lot of the curve is shaded here. There's not much left over. In fact, if I go even farther over to, let's say, 3 standard deviations above and 3 standard deviations below, then I get, the empirical rule tells me this is about 97% of the data. And again, these are just approximates. And you can see there is still some data outside of these. There's only about 3% of the data way outside of those. And actually, I think it's more like 99% of the data. So there's a lot of the data here. But again, I don't really memorize this rule. It's just here if you want it. And what we want to do is we want to actually find out how much is there. So let's talk about finding probabilities for normal distributions. We actually are going to use, you can't do this any other way, but with computers or calculators. You could used to use tables, but we don't do those anymore. And so we're going to use R for doing these, RStudio to do these, because we need some way to do it. What is very useful is what we call a standard normal. Every single one of these normal curves is different depending on what the mean is and the standard deviation. We have what we call a standard normal curve, which has always a mean of 0 and a standard deviation of 1. The symbol for it, for some reason, is a z. Don't ask me why, it just is. And we get something called a z-score or a z-value, which can take any random variable with any mean and any standard deviation and make it into a z. So this formula here is what we call the z-score. It actually will change your values into those. So just to convert one here, let's say I have an x of equal to 12. It has a mean of 15 and a standard deviation of 7. I want to find the z-score. So all I would do is take 12, the x value minus the mean of 15 over top of the standard deviation of 7. And of course I get minus 3 over 7. And then if you want, you can find out what that is approximately using your calculator at this point. So if I take out my handy dandy calculator, which is actually happens to be my calculator on my phone because I don't have a handy dandy calculator, I find out that that's equal to negative, because it was negative before, negative 0.429, let's say, if I go to 3 decimal places. Traditionally, these have been done as 2 decimal places, but you can go whatever decimal place you want. It doesn't really matter. It's negative because 12 is less than 15. 12 is to the left of the mean. So the negative sign tells me that we're below the mean. So x is some variable, whatever that variable happens to be. Let's say it has a mean of 12 and a standard deviation of 2. I'd like to find the probability of being less than, let's say, 14. It helps you to draw a picture sometimes, just kind of see what's going on. So again, I'm going to draw my normal curve. My center is 12. 14 on an axis lives above 12, so 14 is up here. This is the x-axis. And we're saying less than, so we're shading everything below here. And we now need to use RStudio to figure out how to do this. So I'll go into RStudio. And RStudio, you can do this in an RMD file. We're not going to. We're going to actually do this just down here in the console. And I'm just going to do, it's called a p-norm. And I'm going to start off with my 14, I believe is what I had. So if I go back and look at my, what I wanted to do, I had 14. So we're going to go with the 14. We're then going to put in our mean value. Our mean value was 12. And we're going to put our standard deviation value. Our standard deviation was 2. And the last thing we need is what we call lower tail. And if you look at this, if I go back to my picture here for just a moment, I'm looking at being below. So I'm in the lower part of the curve. So lower tail is kind of think of as the lower part of the curve, even though it's got a lot of the curve shaded, it's a lower part of the curve. And so that would be lower tail is true. And I didn't spell p-norm right. That is a problem. So p-norm, and then hit return, and there's your value. You can just, if you're in the console or if you're in an RMD file, you can just copy this. Whoops. Copy this. And then I'm going to go back into where I was. And I can then put that value in here. So that's what it's equal to. That's how we calculate it. And that gives us our probability. So notice our probability is about 0.84 or 84%. And look, there's an awful lot of this curve shaded. So 84% makes sense. Let's now do the probability that x is greater than 8. Again, it helps to just draw a picture a little bit. So let's draw a picture. Again, my center is still 12. I'm up here at 8. I'm sorry, down here at 8. 8 is below. For some reason I was thinking 18. So here I'm up at 8. This time I want to be greater than, so it's everything up this way. And you can kind of use that arrow to help you figure that out, but I'm shading upward. And again, I'm going to go do this in RStudio. So go back into RStudio. And again, it's p-norm. And if you notice when you type p-norm correctly, it tells you kind of everything you want to do. And we're going to start off with our value. Our x value was 8. Our mean was 12. Our standard deviation was 2. And our lower dot tail, well, this time our lower dot tail, if I go back and look, and this is why the graphs are useful. If I go back and look at this graph, sorry, wrong place. Go back and look at this graph. And I notice that I'm not shading the lower tail. The lower tail is down here. I'm up here. So I want the lower tail to be false in this case. So go back here, lower tail equals false. Hit return, and there gets your answer. And again, I can copy and paste this, put this into where I'm working right now. And so I now see that it's about 0.97, 98%. So looking at this, I didn't graph perfectly here because I didn't do my axis here very well, but I can see I've got a lot of the curve graded, shaded. Let's do one more. Let's look at, this time we're going to look at a curve going from 12 to 14. So that would be this shaded here. And now I have a little bit more work that I have to do because I'm looking at this. I don't want, if I just do lower tail is true, I don't want all this. This is, I need to put away. So lower dot tail is true would give me all this area. So true would do all of this, but I don't want all that. I just want this part here. So I need to get rid of this part here. I need to subtract that off because I don't want it. I need to get rid of it. So in this case, we're going to look at the probability that x is less than 12, which is this area. Oh, sorry, let's do the 14 first. X is less than 14, which would be all of this from 14 all the way down. And I'm going to add to that, I'm sorry, I'm going to subtract from that. I don't know why I'm doing it backwards here. Subtract from that the probability that x is less than 12. That part I want to take away. This part right here I want to have go away. So I'm going to subtract these two, and then I go and use my RStudio again. Both of these are less than, so they're both lower tail is true because we're still looking at true stuff over here, but we still have to subtract them. The nice thing is that you can do that straight in RStudio just like that. So we can go back over here. We do p-norm. And we're going to start with the 14. The median was 12, the standard deviation was 2, and lower dot tail is true. Again, we're doing everything below that. And then we're going to subtract from that p-norm. This time 12. 12, the mean is 12, standard deviation is 2, and lower dot tail equals true again. Because again, some people think it's a common mistake I see is to say it's false, but it's again looking at those areas. And in both cases, the area is everything to the left. So now I can go put this back over here, insert this, and I have my answer. And this is about 34% of the curve is shaded. I could have done it knowing that the 12 is actually half the curve. And since the whole curve is 1, half the curve is 50% or 0.5. So I could have just found the 14 and subtracted 0.5. And that would give me my 0.34. But it's easier just to do it this way because you don't always have it be just 12. If I had been over here at 8 or down here at 6 or something like that, I'd want to still do the same process. All right, the last thing we can do is what we call an inverse normal. This is where we have the probability and you want to find the x value or z value that corresponds to it. So in this case, I'm going to tell you that the probability that x is less than x0 is some number. I'm telling you what that probability is. So if you think about looking at a graph, and I'm just looking at a graph real fast here, I don't exactly know what any of these things are. We're going to go ahead and use that same one we've been using with 12 as the center. But I've got some x0 here. I don't know exactly where it is. Just put it somewhere. And we're saying we're less than it. So we're below it because we're saying less than. If we're saying greater than, we shade the other way. And we're saying this area here is 0.37. And I want to find that number. I want to know what number that is on the axis. That's what I'm looking for here. So again, I'm going to go back to RStudio to do this. The command for this is called qnorm. Instead of pnorm, it's qnorm. And it would be, again, I've got my p-value, which is the 0.37. Make sure you put it as a decimal, not a percent. Then my mean of 12, my standard deviation of 2. And again, lower tail equals, in this case, true, because we are shading the lower tail. Anything time you're less than your lower tail, if you're greater than, your lower tail is false. Hit return, it'll come back with your answer. So I can now go put that here. And I now have that my x0 is 11.334, or 3, sorry, let's say 11.34. All right, so there's my x0. There's that x value here on here is 11.4. And that's it. Let's try one more. Let's find the area between a negative z and a positive z is 90%. So this time we're using z's. So that means our center is 0 and our standard deviation is 1. Negative z is less than 0. Positive z is greater than 0. And we're saying that the area between these two is 0.9. Well, again, when doing these, we need to know the area to either to the left or the right. It doesn't matter which one, but let's go with left. So we need to know this area here. I need to find out what this area is right here in order to use Q norm. So I need to figure that out. And I remember I just said the total area under the whole curve is 1. So the area in both of these parts, in this part and this part, would be 1 minus 0.9 or 0.1. Great. So I now know that these both together add up to 0.1. Because of symmetry, this one here by itself is 0.1 divided by 2, 0.05. So that's the value I'm going to put in there as my probability. So I'm going to go back to my Q norm. Don't ask me why it's called Q. I don't know why they picked Q, but I'm going to put in 0.05. My center is 0. My standard deviation is 1. And again, my lower dot tail equals true because we're looking for that part there. And there's my value. And again, I can put that in here. So I now know what this is. This is actually my Z value, my Z0. It equals that Q norm, and it equals negative 1.6448 or 1.65 if you want to. That's the negative one. The positive one, of course, is just positive 1.6545. And that's how we do finding probabilities.